We begin our discussion of Lecture 17 with hybridization. Let's talk about what hybridization is and ultimately what it does for us in terms of molecular structure. Alright, so any particular bond that you may have can be related to the X, Y, and Z directions. And if we focus on the S and P orbitals of like a second energy level atom, like anyone in the second row, we have basically those directions, whether on the Z direction, the Y direction, or the X direction. And then we have the S orbital that's pretty much symmetrical in all directions. Alright, but then the question arises as to how can you use those orbitals to make molecules where the bonds are pointing in different directions altogether. And the way you make that happen is by using a trick of linear algebra known as a linear combination of atomic orbitals, where you basically look at what happens if you mix the orbitals together in order to make a hybrid. And if you look at the picture right here, you have an s orbital connecting with a pz orbital. If you mix them together, you end up forming an sp hybrid. And notice that we have a region of higher electron density because you have areas of equal shading, but the area that has opposite shading ends up having a lower area of electron density. Now altogether this is still pointing up as the pz orbital was going up and down. But you could also combine an additional p orbital. So in the mix, you could add a single p orbital to a py orbital along with the s, and that with another direction that's not going to be in between planes. It could be in the xy plane, the xz plane, or the yz plane. And if you add the third additional p orbital, that's where you get directionality along any position in the 3D scope of the Cartesian coordinate. Alright, so let me show you how this works out. Now in the case where you mix an s orbital with a p orbital, and I'm going to stick to the pz for now, you end up with a hybrid orbital that either points up or down. And this is the same thing as saying we're adding the p orbital with the shaded lobe on top to the s orbital. Or if you say that you're subtracting it, then what you're really saying is that the shaded lobe is pointing downwards. And that's the reason why your hybrid orbital points down. Now another way to look at this is to draw a little matrix, a 2x2 matrix representing the combinations you have here. And simply you look at the signs. Now the s orbital is always going to be positive. So you will always have this plus on the first column representing the s orbital. But what's happening for the p orbital is what's represented here on the second column. So you have the plus and minus. And notice here that for the second row, you have a change going from plus to minus. And that change can only happen if you go through a value of 0. And that value of 0 is what we call the node in the actual linear combination. Now, if you add a second orbital, so here I'm dealing with the px and py, what happens is that you add some directionality to this. But let me show you what's happening here, because now we have a 3x3 matrix. And once again, the first column will always be positive, representing the s orbital. The first row will always be positive, so the same thing is true here. So we have positive, positive, positive. What you basically do is come up with increasing amounts of nodes. So these red regions that I have here are the nodes. Now the last row, it's always going to work out that you have alternating signs. You go from positive to negative, negative to positive, and you have the highest number of nodes, these regions in between where you make the switch from positive to negative or negative to positive. For the middle one, the only way though to end up with a lower number of nodes is to have the node itself on the second column, second row cell, and that means that you have basically no electron density whatsoever on that second atom. So notice here that the px orbital I didn't even include it because it doesn't actually play a role. But what happens is that you end up with orbitals, sp2 orbitals. Notice the notation. We use one s orbital and two different p orbitals, so we end up with an sp2 hybrid orbital. Over here, we use only a p orbital and an s orbital, so we end up with a hybrid sp orbital. With sp2 orbital, we have directionality on the xy plane. This particular orbital looks like it's coming at us, but going to the left, whereas this one right here is going to the left, but going away from us. And the middle one is going straight to the right. If we add the third p orbital to the mix, now we get a 4x4 matrix. Now, like before, and this is your tetrahedral structure, by the way, so once again, that idea of having the central element on the center of the cube kind of plays a role. But looking at the matrix, first row is all positives. Last matrix, everything is alternating, plus, minus, and the first column is always positive. So then what you do is you gradually increase number of nodes. For the second row, you want to have one node, so you have two positives on the left, two negatives on the right. Third row, you want to have two nodes, so you have positive, negative, negative, positive, and you want them to be semi-symmetrical, so that you have a proper distribution, if you will, of nodes. And then the last one has three nodes altogether. So those are the numbers, basically the signs that we see for each of the orbitals, right? So plus, minus, minus, or yeah, plus, plus, minus, minus, plus, minus, minus, plus, plus, minus, plus, minus. And this also gives you directionality to the bonds. Notice that the sp3 that we have here in pink is actually pointing down, but towards us and to the left. The green one is pointing up and to the right, but also towards us. So this is kind of giving you a picture of the 3D outlook of this stuff. And the cool thing is that your SP directionality gives you a linear structure. Your SP2 gives you a trigonal planar structure, and your SP3 directionality gives you a tetrahedral structure. So this is how you get into the different shapes of the molecules. Okay, in the next video, we're going to talk a little bit more about this molecular determination using hybridization.